In this lecture, we are going to talk about friction, and then we have just one more topic left, that is virtual work. The topic of friction as such is very simple, but we are prone to making mistakes in this topic, because as soon as we hear the word friction, many times we are tempted to write that friction means mu n, and that is not right. But actually there are very few concepts, so I'm going to clarify the concepts regarding friction, and then we will do several problems on this. We are talking about what is called dry friction or Coulomb friction. So when the mating surfaces are dry, they are not lubricated, then that is dry friction or Coulomb friction. And friction acts tangent to the contact surfaces. Okay, that is very simple, we know that. And it opposes motion, so it acts opposite to motion, or there may not be motion, so it acts in the direction in which motion could have happened under the influence of various other forces. So it acts opposite to motion or opposite to possible motion that could have happened. There are three scenarios I'm going to differentiate. One is when there is actual slipping. So for example, take this body resting on this surface, and this body is actually moving. So there is relative motion between the body and the surface, so the body is actually slipping. There is friction, and that is called kinetic friction, because the body is actually moving. The friction is called kinetic friction. If we draw a free body diagram of this body, we have its weight acting downwards, and the reaction from the surface, the perpendicular reaction from the surface, that is N, and kinetic friction Fk, it is always given as mu k n, where mu k is coefficient of kinetic friction and n is this normal reaction between contact surfaces, and it acts opposite to motion, because motion is actually happening. It acts opposite to motion. So the idea of kinetic friction is very simple. It is going to be just mu k n, and it will act in the direction which is opposite to actual motion. Equation like this, like we are writing Fk is mu k n, this is called a frictional equation. Another scenario is when there is no actual slipping. So the body is at rest relative to the other surface with which it is in contact. There is no actual slipping. Friction can still be there. And that is not called kinetic friction, that is called static friction, because the body is at rest relative to the other surface. It is called static friction. And within static friction, there are two scenarios. One is the body is on the verge of slipping. So slight increase in external forces and the body is going to slip. It is on the verge of slipping. It is not slipping yet, but it is on the verge of slipping. This is also called impending motion. For example, we take this body. It is resting on this surface. Its weight is W, and a force P is applied to this. As P is increased, we will reach a point at which the body is on the verge of slipping. So if we increase P little bit, and it is going to slip. So that is, it is still static friction. It is not kinetic friction, because the body is actually not slipping, but it is on the verge of slipping. So it is the limiting case of impending motion. With this scenario, friction acts opposite to impending motion. Okay, so there is no actual motion. It is going to act opposite to the impending motion, and the frictional force, static friction Fs, that is given by mu s n, where mu s is coefficient of static friction. Mu s is slightly larger than mu k. Mu k generally is in the range of around 70 to 80% of mu s. Now if we draw a free body diagram of this body, you see here its weight is acting downwards. This reaction, normal reaction from the surface is N, applied force is P, and the frictional force, its magnitude will be mu s N, because there is impending motion. So the magnitude of friction is mu s N, and its direction will be opposite to impending motion. So in this case we know it is going to move towards the right. So friction is going to oppose it. So the frictional force is acting in the left direction. So that is one scenario of static friction in which the body is on the verge of slipping. Okay, let us take another case of the same type when we have impending motion. Now in this case there is a ramp, this angle theta, this body has weight W, and a force P is applied to the body, and it is given that the body is about to move. So there is impending motion. Okay, so impending motion means it is still static friction, and we know that the frictional force at this surface is going to be mu s N. But the question is, in which direction this friction acts? We don't know. Okay, it could act in the direction upward or downward. So we'll have to figure out in which direction it acts. And how do we figure that out? Figure out the direction of motion if friction were not there. So remove friction and see in which direction the body could have moved. So friction is going to oppose that. Friction is acting opposite to that. So that's how we will get the direction. Okay. Now this is free body diagram of the same body but without friction. Okay. And I have resolved its weight into two components, W cos theta and W sin theta. The normal reaction from the surface is N, and the applied this external force was P. So this is free body diagram of the body, free body diagram without friction. Okay. There are two possibilities now. One is if W sin theta is greater than P. Okay. So if W sin theta, this downward force, this is greater than P. So in which direction the body is going to move? It is going to move downwards. So the friction will act opposite to that. It is going to act in the upward direction. So if W sin theta is greater than P, then the situation is like this. We have this frictional force Fs given by the frictional equation mu s N, because this is impending motion, this is going to be mu s N. But now we got its direction. Its direction is opposite to impending motion. It is going to act upward. So again, make sure you understand this, that when we have impending motion, we still have static friction and its magnitude is given by mu s N, but its direction we will have to figure out by trying to understand if the friction force was not there, in which direction the body would have moved. And then the friction is going to oppose that, so it will act in the opposite direction. If we take the other scenario in which W sin theta is less than P. So W sin theta is less than P. So under the influence of these forces, if friction is not there, the body is going to move upward. So the friction is going to oppose that, it is going to act downward. And that is what you see here. So this is frictional force, mu s N, but it is acting downward on the body. Okay, so we discussed so far the kinetic friction, which is mu k N, and it acts opposite to the actual motion of the body. So that is simple. Then there is static friction under the situation of impending motion. So the frictional force is going to be mu s N, but its direction we will have to figure out the way I explained here. Okay, third scenario is the body is not slipping, so it is static friction, but it also does not have impending motion. Okay, so it is static friction but no impending motion. So in this case there is static friction Fs, and it can be anywhere between 0 and less than mu Sn, because when the static friction is mu Sn, that is impending motion, so it can be anywhere between 0 and mu Sn. Okay, and we are not going to use frictional equations. Frictional equations are to be used when we have kinetic friction or impending motion. If we don't have impending motion and it is static friction, then the magnitude and direction of the frictional force actually comes from equilibrium. Okay, we do not use frictional equations. They are going to come directly from the equilibrium equations. Let us take a simple experiment. So we have this body resting on this surface, its weight is W, and a force P is applied to this, and the coefficients of friction are given, mu S and mu K. And let us say to begin with, the body is at rest and P is 0. Okay, and now P is increased gradually. So as P is increased, the initial situation is there is no impending motion. Okay, and if we draw the free body diagram of the body, its weight W, normal reaction N, applied force P, and we have static friction. There is no impending motion, it is not on the verge of moving. We have this static friction, and see, I'm not writing Fs equals mu Sn. Okay, we are not going to use frictional equation. So it is Fs, and you can assume it acts in any direction, it doesn't matter. Now when we write the equilibrium equation for this body, because the body is actually under equilibrium, you get Fs equals negative P by force balance in this direction. So the magnitude of static friction is P, and we got this negative sign, so it actually acts in the opposite direction. So you see, we got its magnitude and direction just by equilibrium on the body, not by using frictional equation. So that is with no impending motion. Now as P is increased, we will reach a point when we have impending motion. So the body is just about to move. We increase P slightly and it is going to move. Okay, so it is still static friction, but static friction now will be given by mu Sn, because that is impending motion. It will be given by mu Sn, and its direction will come from, just try to think, if this friction is not there, in which direction the body is going to move, and this is going to oppose that. So without this friction, the body will move to the right, so this friction is going to act in the left direction, so that is impending motion. As P is increased further, now the frictional force will not be sufficient to keep the body at rest, and body is going to start moving, so we will get kinetic friction, so it will actually slip. So the third case is, as P is increased further, you get actual slipping. So its weight is acting downwards, normal reaction N, applied force P, and now friction, this is kinetic friction given by mu K N, and its direction will be opposite to the direction of the motion. Okay, now let me summarize these with this plot. This is a familiar plot, we all have seen this from actually maybe from 7th or 8th class in school. Now as P is increased, on the x-axis there is P, as this applied force P is increased, it shows the magnitude of the frictional force that is acting on the body. Okay, so initially the friction is static, the body is at rest, and from equilibrium you get this friction equals P. So that is what you see here. So friction equals P, it keeps on increasing. At this point it is on the verge of slipping. So you have the maximum possible static friction that is given by mu Sn. It is on the verge of slipping. So up to this point there is static friction, this point is impending motion, and once it starts to move beyond this point, beyond this P, friction is kinetic, and that is given by mu Kn. So it remains constant, it is mu Kn, and because mu k is less than mu s, once it starts to move, the frictional force actually decreases. Okay, so just make sure you understand. If we have static friction and it is not impending motion, so in this region, then the magnitude of friction and its direction, both of these you will get from the equilibrium equations. You are not going to use the frictional equation. If it is impending motion, so friction corresponds to this point, it will be given by mu s n, and its direction will be opposite to the direction of the impending motion. We'll have to figure that out. And if it is kinetic friction, it will be mu k n, and its direction will be opposite to the motion. Okay, so so the maximum static friction is given by mu s n. Okay, now one question arises, when does motion start? Okay, so let us say we are given this situation. Okay, I know that if the body is moving, then the friction will be mu k n. If it is about to move, it will be mu s n, and if it is not about to move but stationary, I will get this from equilibrium. But how to know at what p the body actually starts to move? Okay, the answer is simple, just common sense. The answer is you take into account all the forces except friction. If all the forces except friction are greater than the maximum static friction that is possible, then the body is going to move. Okay, because see, these forces except friction, they are trying to move the body, and friction is trying to resist it. So if the forces that are trying to move are greater than the maximum friction that is possible, that is static friction maximum, and this is actually mu s n. Okay, then the body is going to move. If we have equality here, then the body is on the verge of moving, and if we have these forces are less than this, then the body is not on the verge of moving. Okay, so it's very simple. Okay, let us do some problems on these. And I'm going to do several problems which have been asked in the GATE exam. The problems are simple, but the topic itself is a little confusing. Okay, this is okay. So in this problem, this is a GATE problem. There is a body of 1 kilogram resting on a surface, and a force of 0.8 Newton is applied to it. And we are given, say, mu s. So initially the body is at rest, and then a force of 0.8 Newton is applied to it. Okay, we are given mu s is 0.1, mu k is also given, say, 0.08. We have to tell how much is the frictional force on the body. How much is frictional force on the body? Okay, so the first thing is you figure out, under the effect of this force, the body actually starts to move or it remains at rest. Okay, and the way to do that is, you see the effect of all the forces. We have only 0.8 Newton here. So if that force 0.8, if this force is greater than the maximum possible friction, which is mu s n, then friction is not sufficient to keep the body at rest, because this applied force is greater than friction. That means the body is going to move. Okay, let us see if that is the case, if the body is actually moving or it is not moving. So we draw free body diagram of the body. its weight acts downwards, that is going to be just mg. Mass is 1 kilogram, so g. We have normal reaction n. By force balance in the vertical direction, n equals g. Okay. So what is the maximum frictional force? Mu s n. That is going to be 0.1 times g. So that is 0.98 Newton. Okay. Now you see applied force 0.8 is actually less than the maximum frictional force that is possible, 0.8 Newtons. The body is not moving. Okay. The body is not moving and there is not impending motion also. So the friction is static friction. It will come from just equilibrium on this. So we have 0.8 Newton force applied to this. So if you show friction at the surface, it is static friction is SF. Okay, by balance of forces you get Fs is 0.8. Okay, so it's a simple problem, but if you don't understand it, we'll be tempted to do, okay, friction equals mu n, and then we'll get a wrong answer. So these problems, they just test our conceptual understanding. They are not difficult problems. Okay, let us do another one. This is also a gate problem. There is a body resting on a surface, and we are given the coefficient of friction here, mu is 0.2. 100 Newton force is applied in this direction, and there is a rope attached to the body which has tension T. So there is force T on this, and its weight is given. Weight is 981 Newton. We have to determine the minimum T. Okay, so that the body just begins to move. It just begins to move. So that is again impending motion. It just begins to move. So we know it is impending motion. So what is friction going to be? It is going to be mu s n. And its direction will be opposite to the direction of motion. See, there is no motion. So it will be it will act in the direction opposite to the direction in which motion will happen if there were no friction. So if we draw free body diagram of this body, we have this is T, okay, 100 Newton. I'm showing all the forces. 981 Newton. There is normal reaction from the surface, so that is N. And then friction. Friction will be mu s n. Without friction, see, the body is going to move to the right because we have force acting in the right direction. It will move to the right. So the friction will act in the opposite direction. So friction acts in this direction. Okay. And it is static friction because the body is actually not moving, but it is impending motion. It will be given by mu s n. So that is free body diagram. And now we can do just the force balance on this. You get in the y direction, you get T plus N is 981 Newton. So you get N is 981 minus T. And do force balance in the x in the horizontal direction, you get 100 is mu s n. So you get 100 is mu s n. That is mu s n is 981 minus T. Okay, so you plug the value of mu in this, that gives you T. So you get T is, let me see if I have the answer, 481 Newton. Okay, so at this tension, body is about to move. If tension is more than this, the body will actually move. And if it is less than this, we don't have impending motion. Okay, Okay, I'm going to do several problems on this. Okay, take this example. This is also a gate problem. And now there are two bodies. And they are 1 kilogram each. And the coefficient of friction between all surfaces at this surface and this surface, both coefficients of friction are 0.3. And a force F is applied to this. And we have to determine minimum F for slip between these two. These two are books. The problem says these two are books. So we have to determine F minimum, so that there is slip between books. Okay, so again, see, this is impending motion. So we know friction, wherever there is slip happening, the friction is going to be mu s n. Okay, let us draw free body diagram of both bodies. Okay, on this body we have its weight acting downwards. That will be mg, mass is 1 kilogram, so just g. And normal reaction from the bottom surface, say that reaction is, let us call that n1. Okay, so those are forces in the vertical direction, and it says there is slip between the books. Okay, so what will be the, see, there for there to be slip between the books, there has to be slip at this surface. Okay, there will be slip at this surface. So there is, so the frictional force here is mu s n, and we will see what its direction is. Okay, let us draw free body diagram for this body. It has force F applied. Okay, from the top, see this, there was this contact, this normal force was N1, so that will be N1 on this. Then its weight acting downwards, it is just G. And at these two surfaces, at this surface and this surface, there is friction. And because it slips, it has to slip at both of these two surfaces. We have mu s n friction at both surfaces. Sorry, I didn't write the normal reaction here. Okay, let us say this is N2. Okay, so the friction at this surface is going to be mu s n2, because normal reaction here is N2. At this surface, normal reaction is N1, friction will be mu s n1. And in which direction they are going to act? See, this force is pulling it in this direction. So if we don't have friction, the body is going to move to the right. Okay, so the forces will act to the left. So both of these are acting to the left. That is free body diagram for this. And free body diagram for this body, if friction on this is to the left, then on this it will be to the right. Because these are internal forces when we between these two bodies, so they have to be equal and opposite. Okay. So now we can do balance. Okay, vertical balance on this body, you will get N1 equals G, and you'll get vertical balance on this body, you'll get N1 plus G equals N2, so N2 will be 2G. And then horizontal balance, this force F is mu s N1 plus N2, that gives us 3G mu s. And I don't have the number, you can plug the number, so that's the answer. Okay. This was also a gate problem. Let us look at another gate problem. Now we have two bodies here, R and S, and mass of R is 100 kg and S is 150 kg. And friction between all surfaces is 0.4, okay, coefficient of friction, and there is a rope attached here. Okay, this thing is fixed, and a force F is applied to this. Okay, we have to determine minimum F so that this body moves. So again, this problem is sort of similar to the problem we just did. So minimum F, so that the body begins to move. So again, it is impending motion. We know friction is going to be mu s n, and it will be opposite to impending motion. Okay. So if you draw a free body diagram of these bodies, okay, this is R and S. On S we have force here. There will be normal reaction. Let us say this reaction here is say R2. Its weight is acting downwards. That will be mass of R, which is mass of S, 150 G. This is 150 G. Between these two surfaces there is contact reaction. Let us say that is acting on this, call this R1, and without friction it is going to move to the right. Okay, so the friction will act in the opposite direction. So at this surface friction will be mu s R1, and at this surface it is mu s R2. And let us see if we missed anything. We got normal reaction and frictional here, normal and friction here, external force and weight. So that's right. And if you draw free body diagram for this body, it will have reaction R1 here. Friction on this is to the left, on this it will be towards right. So this is mu s R1, and there will be tension in the rope. Let us just call that T. And its weight, that is 100 G. So let me separate this so it's not confusing. So these are free body diagrams for these bodies. Now F will be from equilibrium in the horizontal direction. F will be mu s R1 plus R2. So it will be mu s, and see R1 is 100 G. That is based on balance on this. R1 is 100 G plus, and R2 is R1 plus 150 G based on vertical force balance on this. So R2 will be 100 G plus 150 G, that is 250 G. Now we just plug numbers in this, you get 1.37 kilonewton. Okay, so make sure when you draw the free body diagram, you have external forces, and at all contact surfaces like this surface here, you are going to have a normal force and a frictional force. Yes, and also weight. Don't forget that when you draw the free body diagram. Okay, this is another problem from GATE. And in this there is a tongue, a gripper tongue like this. Okay, I can just draw like this. And it is used to hold an object here. There is a pin here, and to hold it in place, these are the forces applied. The forces are applied on this, and this is a pin, and we are holding this object. So let's say this force is F. and the weight of this object is 2000 Newton, and some dimensions are given. We are given, okay, this distance is 0.3 meter, and from here to here this is 0.15, and the coefficient of friction between this body and the tongue, that is it is coefficient of static friction, is given as 0.1. Okay, we have to determine the minimum force, okay, so that we are able to hold this body, it is not going to just slip. Okay. So again, see, there is impending motion. If the force is less than this, the body is going to slip. So this is the point of impending motion. So we draw free body diagrams. Free body diagram for this body here. Its weight is 2000 Newton, and from both these surfaces there are going to be, these are contact surfaces, there will be normal reaction and also the frictional force. Okay. So let us draw them like this. This is N, say normal reaction, this is also N, and friction, we know friction will be mu s n because this is impending motion. It will act in the direction opposite to impending motion. So without friction, this body is going to move downwards. So friction will act in the upward direction. So both of these are mu s n. So by a balance on this body, we can write twice mu s n equals 2000, and that gives us n. We get n is 10,000 Newton. Okay, that gives us n. But we have to determine this force F. So we can draw a free body diagram of this thing. Okay, so let me do that. For the tongue, if we draw free body diagram, and I'm just using, see, it has, if you want to say the arms, it has two arms. I'm drawing the diagram of just one arm. There is a hinge here, so there are some reactions at hinge. Okay, so those are forces in x and y direction. There is force F applied here, and right here, because the body was attached, we are going to have the normal force N, which will be opposite to this. Okay, it will be, because I'm drawing this side. Okay, so F will act like this. It will be, sorry, N will act like this. So this is N, and then frictional force. Okay, on this thing it was in the upward direction, on this it will be downward. So this is mu s n. Okay, so that is free body diagram of this. And now we can take moment. So it's a rigid body, so we can write three equations of equilibrium, but we don't have to do that to find out what we need. If we just take moment about this point, okay, moment about this point, let us say this point is O. So moment about O is 0. Because of force F, moment will be F times this distance. This distance is given 0.3 meter. So 0.3 F. That is moment of this force in the clockwise direction. Plus we have to do this frictional force, mu s n times this distance. But actually in the problem this distance is not given. So we are just going to neglect that. Okay. Because we can assume that this length is much greater than this length. Okay, so the moment of this force here about this point will be negligible, and the information is not given in the problem, so we neglect that. So this will be equal to moment of this force about O. So that will be n times this distance. This is 0.15 n. That is moment balance on O. We already have n, so this gives us F. We get 5,000 Newton. Okay. this one is very simple, but I am doing this so that I can do a relatively more difficult problem right after this. There is a body resting on an incline. Its weight is W, and this angle theta is gradually increased. So initially it is horizontal and theta is increased. At what theta the body will begin to slip? So this one is very simple. So the free body diagram of the body, we can resolve its weight into two components. W cos theta and W sin theta. Normal reaction from the surface, so that is N. And then frictional force. Without friction, this body is going to move down. So friction is going to act upwards. And this is impending motion. At this theta, it begins to slip. So this friction will be mu Sn. So we get N equals W cos theta by force balance normal to the plane. You get N is W cos theta and mu Sn is W sin theta. So we get tangent theta is mu s. So at this theta the body will begin to slip. Okay. Now this was a very simple one, but I wanted to explain one idea through this. Now when we have a body, let us take this on a horizontal surface, and the normal reaction is N from the surface, and the body is about to slip. So the frictional force is mu Sn. This Fs is mu Sn. So the net force from the surface on the body will be this N and Fs vectorially, and that will be directed like this. Okay, that force is directed like this. And if this angle we say is phi s, you see tangent phi s will be mu Sn over N. So tangent phi s equals mu s. Okay. This phi s is called angle of static friction. This angle of static friction. So this is the angle that the resultant force makes with the normal. And see, here we got the answer, tangent theta equals mu s. So theta is actually phi s. Okay, so the body will begin to slip when this angle theta equals angle of static friction with phi s. And you can also think of this experiment as a very simple way to determine mu s, because we can keep on increasing angle theta and it begins to slip at some angle theta, and mu will be just tangent of that angle. Okay. Okay, now I want to use this to explain a relatively more difficult problem. Okay, this is not a gate problem. Let us say there is a body on incline. Its mass is m1, angle theta, and the coefficient of friction here, static friction here, is mu s. There is a pulley here, and pulley is frictionless. Okay, for a frictionless pulley, let's say I have a rope going like this, and a force P is applied at this point. Okay, for a frictionless pulley, we discussed this, that if tension here is P, then tension here is also P for a frictionless pulley. If there is friction, that is different. We'll talk about that in a while. Okay. Now we have to determine minimum P at which body begins to move. Okay. At which you can say the body remains stationary, the minimum P at which this body remains stationary. So if we decrease P slightly below this, it is going to move. So again, this is the case of impending motion. Let us draw free body diagram of the body. Okay, its weight m1g, and I'm resolving that into two components. Okay, just directly. This will be m1g cos theta, and this will be m1g sin theta. That is weight of the body. And then there is force P in this rope here, normal reaction from the surface. Okay, let us say that is N. And frictional force. Okay, we know frictional force will be mu s n because this is the case of impending motion. But in which direction? The problem says we have to find minimum P at which we are able to hold it stationary. Now if P is less than that, in which direction the body will move? It will move down. Okay, because we are barely holding it with this force P. So if we decrease it slightly, it is going to move, but because we have less force here, it is going to move downward. So the friction will act in the upward direction, opposite to that. That is mu s n. Okay. And now we can so that is the free body diagram. And now we can write the equations here. You see, we'll have N equals m1g cos theta by force balance in the vertical direction, and this P plus mu s n equals m1g sin theta. And you can substitute n here, and you get P is mg sin theta minus mu s mg cos theta. Okay, so this is the minimum force that has to be applied to keep the body at rest. This is minimum. Okay. Now let us say it says the maximum force that can be applied so that the body is still stationary. The problem is that, okay, we have to find, instead of P min, we have to find P max. Okay. Okay, now the free body diagram. See, all these forces remain in the same way. This will be mg sin theta, mg cos theta, normal reaction N, this force P because of the rope, and now friction mu s n. We have to find maximum P at which the body is still stationary. But now think about this. Okay, so we are applying P here. We have increased this to the maximum so that the body is still stationary. So if we increase it beyond that maximum, in which direction this body will move? It will move in the upward direction because we are applying the force more than the maximum at which the body is still stationary. It is going to move upward. So now friction is going to act downward. So that's the only difference. So friction acts downward, and it is impending motion. It will be mu s n acting downward. Okay, so when you do balance on this, just like we did for the first case, you'll get P max equals mg sin theta plus mu s mg cos theta. Okay, so again I want to emphasize that with impending motion, you see in these problems there was impending motion. So we used frictional equation that the static friction is mu s n, but you can't assume it in any direction. Okay, you have to see in which direction the body is going to move, and the friction will be opposite to that. So and that was in opposite direction in these cases. Okay, so let me also draw, if we plot for this problem frictional force F versus P. So let us say this is P min we calculated and this is P max. And say we assume that this is the body at angle theta. If I'm assuming that friction is positive if it acts downward, okay, so this friction I'm going to take as positive. Just arbitrarily I'm saying that is positive. Okay, now let us see. If force is less than P min, if P is less than P min, body is going to move. In which direction it will move? It will move downward. Okay, it will move downward if force is less than P min, because this is the minimum force to keep the body stationary. It is going to move downward, so friction is acting upward, so friction is positive. Friction is positive, and because the body is actually moving, it will be, let me repeat, the body is going to move downward if P is less than P min. Then friction will act upward. Okay, so friction is negative, because upward we are taking as negative. It will be negative, and it is kinetic friction, so it will be this, like this, and this is mu kn up to this point. If P is greater than P max, the body is again going to move, and it is going to move upward. So the body is going to move upward, friction on this is acting downward, so friction is positive, and this is again kinetic friction because the body is actually moving, so it is positive, and this will be like this, mu kn. Okay, now if P is just P min, or just slightly less than this, you take the limiting case, so it is P min, so the body is stationary, it is not moving, but it is about to move. The frictional force will be static friction, and it will increase. Actually, this will be mu Sn. Okay, similarly at this point, this will be mu Sn, and between these 2 points, okay, it is static friction. If P is between P min and P max, the body is not going to move, it is going to remain stationary, and friction is static friction, and it will vary like this. Okay, so again, I hope you understand that if we have a kinetic situation, friction is mu kn, and it will act opposite to the direction of motion. And if we have static situation, which will be between P min and P max, okay, friction can have any value between 0 and mu Sn, and its magnitude and direction, both of those we get just from equilibrium equation. That will be like this. Okay, now there is a slightly different idea I want to present. Okay, now consider this body resting on a surface. Its weight is W and force applied is P. And I'm just drawing its free body diagram. Okay, weight will act through. Now see, up to this point we did not consider through which points these forces are acting. We just took force balance in X direction and in Y direction, and for that it does not matter at which points these forces are acting. But if we want to do a moment balance on this, then it matters at which point those forces are acting. So now we are going to look at it from that point of view. So its weight W will act through its center of gravity. Okay, say force P is applied here, okay, from this point, and frictional force that acts on this surface, so its line of action is along this, and it will be opposite to this, that is Fs. Okay. and we know normal reaction acts vertically up. But let us see at which point normal reaction will act. Okay. You see, these two forces P and Fs, they are opposite, and for equilibrium they are equal, they are parallel, so they form a couple. So these two forces P and Fs, they have a clockwise movement on the body. Okay. So the body is going to rotate unless the other forces have a counterclockwise movement. Now, other forces are this weight W and normal reaction N. That means this normal reaction N cannot be below W. It has to be to the right of this. Okay. Because now these forces W and N, they are equal, they form a couple, and they form a counterclockwise couple. Okay. So we were doing force balance, P equals Fs, W equals N. Now looking at this from moment point of view, if this distance is, let us call this say A, and this distance between P and Fs, if this vertical distance is B, then moment balance requires this PB, okay, that is moment of these two forces, equals WA. Okay, that equals WA. Now what happens, see, B is a constant, okay, B is a constant, W is a constant. What happens as we increase P? As we increase P, then A increases. Okay. So the normal reaction is going to act more and more to the right. It is going to shift more and more to the right. Okay. And say we reach the limiting situation where normal reaction is now acting at this point. It cannot go beyond this point on the body, that is the extreme. So normal reaction is acting on this point, weight from the center of gravity, Fs and P. It reached this point. And let us say even at this point, this force Fs, okay, or you can say instead of Fs, let me say P. Okay, if P is greater than, less than mu s n. Okay, so this is the situation. If the normal reaction is at this point and still P is less than mu s n. So if P is less than mu s n, applied force is less than the maximum possible friction. So the body is not going to slip up to this point. Okay, so the body has not slipped, and it is not on the verge of slipping. Okay, but it is on the verge of tipping, on the verge of turning. It is on the verge of turning, because if we increase P, this frictional force, it has not reached its maximum yet, so it can balance it. It is not going to slip. Okay, but the moment, see, this PB will be greater than WA, because we have reached the maximum possible A. So the moment of this force will actually be greater than the other moment of these two forces. So the body is going to tip. Okay. So the condition for tipping, if you want to write, you can say two things. One is this applied force P, which is equal to Fs, is less than mu s n. So the body has not slipped. and the other is normal reaction now is acting at this point, so it cannot go beyond this. So if we say this point is A, so the moment about point A, which is you can write as PB minus WA. Okay, this moment is just 0. Okay, so you get P is WA over B, and we have P is less than mu s n. It is less than mu s, and n is same as W. So you get some condition. Okay, that is the condition for tipping. And now it is easy to understand. If the coefficient of friction is large, okay, mu is large, then there will be more tendency for tipping than for sliding. If B is large, the body is tall, then also there will be more tendency for tipping. Or if A is small, then also there is more tendency for tipping. So make sure you understand those based on the analysis we did here. Okay, this was, let us say this was problem number 34. We just found out, okay, what is condition for tipping. Just 2-3 more problems I'm going to do. Actually, this also I think it's a gate problem most likely. In this problem there is a ladder at angle theta, and its weight from the center of gravity, its location is given where it acts is W, and we are given the coefficients of static friction at this location, and this say A and B is mu s, coefficient of static friction. Okay, we have to determine minimum mu. Okay, so that there is no sliding of the ladder, for no sliding. So again, this is the case of impending motion. So the free body diagram will be there is normal reaction at A, at B. These walls are not smooth, okay, they have friction. If wall is smooth, then we will only have normal reaction, there will not be any friction, but in this case we have friction also. Okay, with W acting here, and now friction at these two locations. Okay, now it is impending motion, and when it slides, actually it is going to slide at both of these points. Okay, and so it is going to slide, you see, like this. It is going to fall down. So without so friction will be in the opposite direction. So at this point friction will be mu s n A, and here will be mu s n B. So now we can find out what is asked, because you see how many unknowns we have here. We have 3 unknowns, NA, NB and mu. Okay, there are 3 unknowns, so on a rigid body we can write down those equations to find those out. I'm not going to solve it, but just wanted to show you the free body diagram, and that these will be mu n, and in the direction opposite to in which motion is going to occur. Okay, now this next problem is slightly more complicated. So in this there are two bodies, M1, it has mass M1, and M2, they're resting on this surface, and the coefficient of friction between M1 and M2 is mu1, and between 2 and this surface is mu2. They are different, and a force P is applied to the body. And say it is given to us that no tipping occurs. Okay, so we don't have to test whether tipping occurs, because in a previous problem, I hope you understood when I explained that there is a possibility that body can tip before it begins to slide, and that will be a situation when the normal reaction reaches the extreme point, okay, on the body. It cannot move any further, but slipping has not yet started, so then the body is going to tip. So in this problem, say it is given that there is no tipping. We have to find minimum P at which, okay, slipping occurs. Okay, minimum P at which slipping occurs. Okay. Now in this problem, actually you will have to consider various scenarios. See, one possibility is there is slipping between 1 and 2. Okay, so this body, 1 starts to move, but 2 does not move. 2 remains at rest. That is one scenario. Okay. Other scenario is if M1 and M2, they together start to move. So there is no slipping between 1 and 2, but it slips at this surface. There are two scenarios. So I'm not going to solve this problem with numbers, but just going to formulate this. In a real situation, you might be given numbers, and then you'll have to consider both scenarios, and the minimum P at which slipping occurs will be the minimum you get by considering both of these scenarios. Let us consider possibility 1, when we have, say, slip between bodies. Okay, there is slip between 1 and 2. Okay, let us consider this situation first. Now we draw free body diagram for body 1, and okay, so this is 2. Various forces are, there is P here, and weight downwards, that is M1G. Normal reaction here, let us call that, say, N1, and by force balance in this direction, I'm just writing it directly, this will be M1G. And if there is slipping between 1 and 2, okay, then you see the body is moving to the right, so there is this static friction, the impending motion case, okay, it will act in the opposite direction. It will be given by mu s N1. That is free body diagram for this, because slipping just begins, so that is impending motion. And free body diagram for this one, there is N1 here. Actually, I should have drawn them a little bit apart for you to understand clearly. And this friction was in this direction, so on this body, okay, we'll have friction mu s N1, and its weight M2G. Normal reaction from this surface, okay, so this is N2, and this is going to be just by force balance in the vertical direction. It will be N1 plus M2G, and N1 is M1G, so actually N2 will be M1 plus M2G. Let me just write that. And see, this force on this is on the right direction, so if there is no friction here, the body will move to the right. So the friction here is opposing that. Friction is acting in this direction. Okay, but we had slipping here, not here. Okay, so don't write this force is mu n. Okay, slipping was between 1 and 2, not between 2 and the bottom surface. So this frictional force, let us just, it is still static friction. Okay, call this Fs, and it will come from equilibrium. Okay. Now we write down the equation. Okay, balance on this will give us this P equals mu s n1, and n1 is m1g, so it will be mu s m1g. Okay, and balance on this will give us mu s n1 equals fs. So I can write fs equals mu s n1, which is mu s m1g. Okay, m1g. Okay, but see, we assumed that there is slipping between 1 and 2, but no slipping between 2 and the surface. So what is the requirement for that? The requirement for that is this force, or this frictional force. This frictional force Fs has to be less than maximum possible frictional force. Okay, because if the body can supply Fs max here, this Fs, for it to be stationary with this equilibrium, has to be less than that. Otherwise the body is going to slip. Our assumption is going to be wrong. And what is Fs max? This is less than Fs max. So less than Fs max. Fs max will be mu2 n2. Okay, and n2 is m1 plus m2g. So mu2 m1 plus m2g. Fs has to be less than this, but Fs is mu s m1g. So we got mu s. Okay, I took this one as mu s. Okay, this one I took as mu s, and this I took as mu2. Okay, I should have taken this as mu1, but anyway, I hope you understand. This I took as mu s between these two surfaces, and between these two surfaces I took as mu2. So mu s m1g is less than mu2 m1 plus m2g, and P equals mu s m1g. So if this is true, then there is going to be slipping between 1 and 2. Okay, so if numbers are given, we'll have to calculate, okay, P equals this, and we have to also verify that this number is less than this number. Then we can say that our assumption that slipping happened between 1 and 2 is right. Okay. Now let us take the other possibility when there is slipping between so we are slipping right here. Okay, now so you can draw this like this. Okay, these are two bodies, and I'm going to quickly draw the free body diagram. Okay, this force is P, this is m1g, n1, and now the friction on this is static friction, but there is no impending motion between 1 and 2. So I'm just writing this as Fs. Okay, don't write this as mu n. Okay, at this surface we have n1. This force is Fs. There is m2g, and the normal reaction here, n2, will be n1 plus m2g, that will be m1 plus m2g, and friction here, because now we are saying slipping occurred here, so this force here, this will be mu n, this will be mu2 n2. So that is the free body diagram. Okay. And if we do the balance on the entire thing, okay, I'm going to write equation considering this entire thing. So this N1 and Fs, they will not be in the equation, they will become internal forces if you are writing for the entire thing. So our equation will become, in the horizontal direction, we get P equals this. We get P equals mu2 m1 plus m2g. Okay, so this is when slipping occurs at this surface. But now we will have to verify that this is actually true. For that, this force here, Fs, this force has to be less than the maximum static friction possible here. Okay, and the maximum, you know, will be mu s n1. That is maximum. So you can write, because this Fs is same as P, you can write P is less than mu s n1, and n1 is m1g. So instead of this, let me write P is less than mu s m1g. Okay. So if this condition is satisfied, and this, okay, then the slipping will be at this surface. Okay, so I hope you understand that sometimes we have a problem in which there are multiple scenarios possible, and then we have to consider them separately and see which one gives us the minimum P required, as with this problem. Okay, let me do one more problem along similar lines. Number 37. Okay, so we are given these two links connected by a pin at this point, and they are resting on a surface. Okay, so this is A, B, C. All the dimensions are given, and a force P is applied at this point. Okay, they have weights. Let us say this is W1. Okay, and the weight of this member acting through its center of gravity, wherever that is, say W2, and we are given coefficient of friction at A is 0.3 and coefficient of friction at C is 0.5. Okay, we have to find minimum P so that it begins to move. Okay, minimum P so that it begins to move. Now, actually, without going into all the details, you see, if we draw a free body diagram for this entire thing, okay, there will be, you see, two forces here, normal and frictional, okay, and two here, okay, and we have this external force applied here, P. Okay, I'm going to separate them into two. Now, the free body diagram will be at this. Because of pin connection, we'll have some horizontal force, okay, vertical force, and forces on this will be opposite to that. So say this is Bx, By. Okay, this weight we had W1, the weight of this one W2, this force applied P. We have normal reaction at A and A, and normal reaction at B and B. And see, actually in the problem there are different scenarios. Okay, one scenario is because of this force P, there is slipping at A but no slipping at C, or there could be slipping at C and no slipping at A, or just a limiting case will be when there is slipping at both of these points. Okay, so there are different scenarios and we'll have to evaluate them. So I'm writing here friction as Fa and here friction as Fb. So there are two bodies now. In total, we can write 6 equations of equilibrium and see how many unknowns we have. I haven't used any frictional equation yet. Okay, I'm just writing them as Fa and Fb. I haven't used frictional equation that F equals mu n. I haven't used that. So how many unknowns we have? By, bx, p, na, nb, that is 5, and fa and fb. There are total 7. Okay, there are 7 unknowns. And we can write 6 equations of equilibrium, 3 for this, 3 for this. So 6 equations we will have from equilibrium. Okay, so we'll need one more equation, and that one more equation will be the frictional equation. So don't assume that this Fa is mu s Na and Fb is mu s Nb. No, because we have 6 equations from equilibrium, we just need one more equation. There can be slipping at A or slipping at B. Let us say I assume slipping at A. That is my assumption. So then we can write Fa will be mu s Na and it will act in this direction. Okay, because it will move in that, so it acts in this direction. That is slipping at A. But then we will have to verify. So we got now 7 equations, 6 from equilibrium and 1 this. We have 7 equations, 7 unknown we can solve. But we'll have to verify that Fb after calculations is less than Fb max, and Fb max will be mu b Nb. We will have to verify this. Then our assumption that there is slipping at A is true. Or other scenario will be we assume there is slipping at B. Then you will do Fb is, this will be mu A actually. Okay. That Fb is mu b Nb, and we'll have to verify that Fa is less than mu A Na. Okay, so again, just to give you an example that you can have a situation in which multiple scenarios are possible, and you then consider each of those separately. Okay, so don't just assume that frictional force is mu n and then start doing the problem. Okay, I will talk a little bit about frictional forces on belt. Now, what you have here is, let us say we have a curved surface. Okay, only a portion of that is shown. For example, it could be a pulley. Okay, a curved surface, and a belt, a flat belt is on it. Okay, that is shown with black color here. That is the flat belt. And the angle enclosed here from the tangent points, okay, right here and right here, this angle is beta. And we have relative motion between this belt and the surface. There is relative motion. So relative motion means now that there is friction. Okay, so there is friction between this belt and the surface. And if the motion of the belt relative to the surface is in this direction, the relative motion for the belt is in this direction, then friction on the belt is going to be in the opposite direction. That will be, okay, in this direction to the right. Frictional force will be in this direction. Okay, so we will get T2 has to be greater than T1, because T1 is tension here and friction on the belt is acting in this direction. So the tension here will have to compensate for T1 and also for friction here. So T2 has to be greater than T1. And we want to get a formula that will give us a relation between T1 and T2. So that is the idea. And there are different possibilities. For example, this could be fixed and this belt is about to slip on this, or it is actually slipping. That is one possibility. Or other is this pulley, for example, this could be rotating, but still there is relative motion between the pulley and the belt. So for friction, what matters is relative motion. So both are moving, but if we have relative motion, there is going to be friction. Okay. If we take a very small portion of the belt that you see here, and we draw these lines perpendicular here, and say this enclosed angle is d theta. Okay. Enclosed angle is d theta. We are going to draw a free body diagram of this. Let us say this is y direction, so this bisects this angle d theta. Okay, so just through the middle of this we have this y direction, and x direction is perpendicular to this. Okay. Now what are the forces acting on this? The forces are, there is tension T at right here, okay, that is shown here, and because this angle here is half d theta, and tension will be perpendicular to this, okay, so tension acts in this direction, so it is at an angle of half d theta from x direction. Okay, tension here, say that is T plus dt, and that is perpendicular to this. So again, it will be at an angle of half d theta from x direction. So those are tensions. Because belt is in contact with the surface here, from the surface we will have a normal component of reaction. That component, say, is dn, and it acts in y direction. And there will be a frictional force. If the relative motion of the belt is in this direction, then the friction on this will be in the opposite direction. Okay. So that is shown here. This is frictional force. It will be mu times this dn, that is frictional force. And we are neglecting the centrifugal force, because actually if the belt is rotating, there is also centrifugal force. We are just going to neglect that. So that's the free body diagram. And this mu could be mu s if the belt is about to slip, or it will be mu k if it is actually slipping. Okay, so we can substitute mu s or mu k for mu. Now when we do force balance on this in x and y direction for equilibrium, and we are also neglecting the inertia of the belt, we are considering its mass is negligible. Okay, so sum of forces in the x direction is 0. That gives us T cos d theta by 2 plus mu dn, this frictional force, minus T plus dt cos d theta by 2. That is what you see here. That is 0. That is sum of forces in the x direction is 0. And we can do, because d theta is very small, okay, in the limit it approaches 0, then cos d theta by 2, this approaches 1. So we can take this as 1 and this as 1. Okay, so with that you get this equations gives us mu dn is dt. Okay. Similarly, we can do force balance in the y direction. We'll have, okay, components of t plus dt and t in the y direction, and also this dn in the y direction. So when we do force balance on this, you get dn minus t plus dt sine d theta by 2 minus t sine d theta by 2 is 0. That is force balance in the y direction. And because d theta is small, instead of sine d theta by 2, we can just write d theta by 2, because when theta is small, theta approaches 0, sine theta approaches theta, where theta is in radian. Okay, it is not in degree, it is in radian. So if we do that, and we neglect the product of dt and d theta, because that is a higher order term, it's very small, we can neglect that. You get dn is t d theta by force balance. We can combine these two equations. That gives us dt over t is mu d theta, and we integrate this from t1 to t2. So we had taken this small section with angle d theta. So if we integrate this, okay, for this entire angle beta, where tension is t1 here, tension is t2 here, so we do that. So the integration on this gives us T2 is T1 e to the power mu beta, where beta is the angle in radian, but that is not in degree. Okay. So that is when we have frictional force on a belt, then the tension in the belt is not same. Okay, we get this relation. T2 is T1 e to the power mu beta. Let us do one problem on this. So there is a mass of 150 kilogram on a horizontal surface, and the coefficient of friction here, okay, mu s is 0.58, and there is a fixed, okay, let me first draw, there is a belt here and then a fixed, you can think of a fixed pulley. This is fixed and belt goes around it. That's belt. And this angle between tangents at these 2 points, okay, this angle is 60 degrees. So if I say this angle beta is 60 degrees. And the coefficient of static friction between the belt and this pulley is, say, this is say mu s1 is 0.9. We have to determine the minimum force F so that we can move this block. Okay, the minimum force F so that we can move this block. Okay. Now you see, there is friction acting here and there is also friction acting here. Okay, because this is fixed, there is impending relative motion between this and this. Okay, so how to do this problem? If we draw a free body diagram for the block, its weight is 150 G, and let us say tension in the rope here is T1, normal reaction N will be 150 G, and if it is about to move, then the frictional force will be mu Sn and it will be in the opposite direction. Okay. So this will be mu s is 0.58, it will be 0.58, and normal reaction is 150 G times 150 G. So that is the situation with this block. So you get T1 is 0.58 times 150 G. That is T1. Now, if we take free body diagram for the belt around that pulley, that belt goes like this. So it has force T1 here, we already got that, and this is T2, and this angle was beta. Okay. So because of friction here, see, relative motion of the belt is going to be in this direction. So friction acts in this direction. This is the direction of friction. Okay, we have to see in which direction friction acts. So then T2 is greater than T1. So T2 will be T1 e to the power mu beta. We got that relation previously. So T2 is T1 e to the power mu s1 beta, and that becomes 0.58 times 150 G times e to the power mu s1 is 0.9, and beta we have to take in radian. This is 60 degree, so that is pi by 3 radian times pi by 3. So this will be the answer. Use plug numbers in Newton. So this is the minimum force that is required to move this. Okay. I'm going to stop at this point. So in this lecture, we just discussed the concepts regarding friction, that there is kinetic friction and impending motion. You have the limiting static friction, and otherwise you have static friction, and how to solve those problems, and also talked about this belt, when you have frictional force acting on the belt. So those are concepts of friction. But in terms of solving actual problems, the idea of friction is applicable to many machine elements, like belt drives and power screws, brakes and clutches. So all those things we are going to discuss when we talk about design of machine elements. I'm not going into that right now, but for those topics we won't need any fundamental understanding. We already discussed the fundamental understanding of friction. We are just going to apply what we understood in this lecture to brakes, clutches, power screws and belts. So that will be application which will come in design of machine elements. I'll stop at this point. Thank you.